Great. Thank you very much, Nate. And I also want to acknowledge that most of the research I'm going to present was done while I was a PhD at Northeastern. So that's why there's 3 affiliations up there. So this is the meeting of the waters, where 2 rivers in the Amazon run together for several miles. I like this picture. And there's a connection to gradual typing. So there's this long-standing debate in programming languages between typed and untyped. Should my language have this or that? And it's a contentious issue because the language designer is the one with the power to choose. Once you pick one of the 2, you're stuck with it forevermore, and all of your programmers are stuck as well. So the great idea with gradual typing is to somehow combine the best of these 2 worlds into the same programming language, and now give programmers the power to decide whether they want types in some contexts or no types in other contexts. Of course, it's an excellent idea, and it's no surprise that it's spawned many, many languages, both in industry and academia, and this is just a few of these. That's all very exciting, but there's a huge problem. These languages are all gradually typed in the sense that they agree we should have some parts of the code that are statically checked and other parts that are not. But they completely disagree on what the semantics of types should be. So these languages are firmly divided into 4 camps: concrete, transient, erasure, and natural. And there's a good reason why we have these 4 camps, and it's because there's a difficult trade-off to navigate between the expressiveness of the typed-untyped combinations that we want to allow, the guarantees that types provide to help us reason about programs or not, and the performance cost of enforcing these guarantees. We're not going to talk about this concrete style today because it limits the interoperability with untyped code. So it cuts down on expressiveness. We're also not going to talk about erasure, otherwise known as optional typing, because these types are not sound at all. They're only used for static checks, and they have no influence at runtime. We are interested in these other 2, natural and transient. And yes, the quick explanation is that natural gives you slow but strong types, and transient gives you fast, wrong types. And the label that I use to talk about the specification is deep types on the natural side, shallow types on the transient side. So deep and shallow are the guarantees that we expect these types to provide. Natural and transient are the implementation strategies that give us these. So what we'd like to do is take these 2 parallel worlds of gradual typing and combine them into one. Can we somehow have natural and transient interoperate in the same programming language? And there are many reasons for doing this. First of all, we now give programmers the power to decide between these fast, wrong types and these slow, strong types to navigate the guarantees trade-off. And it should also ease the performance bottlenecks that we've seen in the past, because both of these have complementary strengths. And best of all, there's going to be no change to the surface language. If you've got a program that type checks using the deep types, it also type checks with the shallow types. We have the same language of types on both sides. We only change the runtime behavior. And this work is also orthogonal to basic improvements to both deep and shallow. So work like Picket and Corp Survivor is going to work under the hood to make both of these better in parallel, and we can combine them and still reap the benefits. So this is the goal. And the key question we need to answer in order to get there is decide, what do we do at the boundaries between deep, shallow, and untyped? How do we enforce types here in a way that guarantees the formal properties that we've come to know and love? Deep types satisfy both type soundness and an additional property called complete monitoring, which makes these gradual types compositional guarantees that we can trust all throughout the program. Shallow types satisfy type soundness and nothing more. And on the untyped side, we're expecting a safe, dynamically typed language. So these are the 3 pieces that we'd like to stay faithful to what they've been before when we have the mix. So first things first, let's look closely at the ingredients that we're combining. How does this natural semantics give us deep types, and how does the transient semantics give us shallow types? So the idea with natural is to keep a strict separation between these 2 worlds. And we're going to do so by using wrappers whenever a higher order value tries to cross the boundary. So for example, if our typed world is expecting a function from int to int, and the untyped side sends over a function, we will not let the function cross the boundary. Instead, a wrapper or a proxy value goes across the boundary instead. And now this gives the typed side controlled access to that untyped function, and it's able to check the results that it computes. Similarly, in the other direction, if we're to send a mutable data structure across the boundary, we won't send the data structure off to untyped to let it mutate it. Instead, we'll send a proxy, send a wrapper. So now untyped code can't write things that don't belong in this data structure. So that's the idea, and we keep these 2 worlds very separate with natural and transient. with deep types via natural. Now on to shallow types via transient. And this is a totally different world. The first step with shallow transient is to get rid of wrappers altogether because they have a huge cost. There's allocation, a layer of indirection, and there's also the checking cost. So we're not going to use wrappers, and instead we'll change the typed code, we'll rewrite it to have lots of little shape checks all throughout. So the first step of this shape check strategy is what happens at the boundary. So again, suppose we're expecting an int-to-int function. Untyped sends a function at the boundary. We'll check the shape. So we see this is a function type. We'll check that we have a function value. And since it matches, we let that function go right across into typed code. Similarly, if we're sending a mutable data structure from untyped over to typed, we check that it has the correct shape and then let it cross just as it is. Similar thing happens in the other direction. If we're to send a function from typed out to untyped, untyped code gets access to this typed function. So how on earth is this sound, since we have this checkerboard world now, where untyped values are mixing in our typed code and vice versa? Well, the answer is to have additional checks, not just at the boundaries, but all throughout our statically typed shallow module. So that's what these magnifying glasses indicate. We're going to need, for example, to check the result of every function call on the shallow side, and also check the data that we're reading out of these data structures. So now, to tie all three together, we're going to keep the natural and transient semantics. So first of all, at the deep untyped boundary, we'll need to wrap, just like before. Keep the strict separation that we had initially. On the shallow untyped side, we'll also do the same strategy. Do these lightweight shape checks and checks throughout the shallow typed code. So this means now we have this mingling of values between the shallow world and the untyped world. And that means we have an interesting situation over at our third question mark. It's tempting to say that since deep and shallow are both statically checked by the same type checker, they're both typed code, there should be no cost to them interacting. But if we were to do that, that would be very dangerous territory. So let's go through two examples. What if there were no checks between deep and shallow? Well, for one, deep cannot trust a value that's coming into it from shallow code. So here at the top, we have shallow typed function. So it's defined in shallow code, it's type checked, it's a function that takes in a number and returns a number. What if we send this function out to untyped code? So now f1 is an untyped function that's equal to this shallow typed f0, and send it back in to shallow code at a different type. So before it was labeled int to int, now it's labeled string to string. And we have an interesting situation where the types claim that our f2 here is a string to string function. But the only thing we've checked at runtime is that f2 is a function. Shallow is lazily going to verify that this function computes good results if we call it in shallow code. But if instead of doing that, we pass it off into deep, now we're in trouble. We have deep types that believe we have a string to string function, and that's definitely not the case. So we need some kind of a check between deep and shallow here. As another example, shallow can also misuse a value that came from deep originally. Here we've got a deep type function g0, takes in an int to int, and returns a number. We can send that off into shallow, and so far things are fine. But if shallow type code sends that off into untyped code, and there's been no protection over our function initially called g0, now called g2, bad things can happen. Untyped values can sneak into our deep context, and we no longer have the separation that we wanted. So what to do? Without a sophisticated analysis for knowing which values flow where, what we'll need to do is wrap when values cross from the deep world into the shallow world. And from here, things are smooth. In the paper, you can see the model where we work this out and our arguments both for type soundness and complete monitoring say yes, the deep and shallow worlds can interoperate with one another, preserving their formal properties. Also in the paper, we have a few words about the implementation where we realize this in typed racket. First, I want to acknowledge implementing shallow for typed racket alone is the subject of a separate paper, so you won't find that here. But what we do talk about is there were many challenges in tying these three together. I promise you, though, in the paper itself, there's no racket-specific details. These are general lessons that you would need in any sort of three-way language, we believe. No macros in particular. Okay, so let's move on to the payoff. There's something to say about all three sides of the trade-off, guarantees, expressiveness, and performance, but I know you're all itching to hear about one of these, so let's move on to performance. First, we care about performance of a type system. So what does that mean? We start off with these benchmark programs, the GTP benchmarks. There's 21 of these, but each program opens up a space of possibilities because we have a gradual language, and also because we now have a three-way gradual language. So for example, if we begin with one program that has 3 components inside, in this picture, there are 3 typed components. Since we're in a gradual language, each of these could be modified later on to be typed or untyped. And we care about the performance of all the combinations. So just looking at this switch between 2, we now have a lattice of 8 possibilities. And since types in this paper can now be deep or shallow, we're looking at a 3-way lattice, 3 to the n. So there's 27 points that we care about out of this program with 3 components at the start. So this is the search space that we're looking at that we care about performance. The first question to ask is, how many points out of these lattices run fastest if we use a mix of deep and shallow? So in other words, does the mix matter? Do we really want both in the same program? So we're doing an exhaustive search here over all points, and it's a surprisingly high percentage of these that pay off the best. Come see me afterwards if you'd like to know the details, but we were amazed at how high these percentages are. A second question, and this is where the deep and shallow mix really shines, is what is the worst case overhead now that we have the freedom to choose between the guarantees and performance? Here are the numbers, and these are very good numbers when we're allowed to mix deep and shallow, especially when you compare to what you're stuck with using deep types alone or using shallow types alone. So the middle column says what's the worst case overhead using deep types, and you see these are off the charts in some cases. And even in the shallow side, if you're stuck with shallow types, you're paying more for every line of typed code that you have. So when the program gets towards fully typed, there's a higher cost. So in some cases, we're moving from 4x overhead worst case in shallow down to a 2x overhead, being able to switch between shallow and deep. The one benchmark that we're not happy with is Zombie, and come see me after if you'd like to know the details. But the general lesson is, if you're migrating a program towards untyped up to type, shallow types are typically what you want in the middle of this space, where there's lots of interaction going on between typed and untyped modules. And the deep types are the best once we've turned all the critical boundaries into type channels. Now we can maximize the benefits and get the most out of our type-directed optimizations up in the deep world. So to wrap up, we've seen that different gradual typing strategies exist, and it's for good reason. It's not just an accident because we have different languages like JavaScript and Python, but it's because there's this fundamental trade-off between 3 things that we care about. What we've looked at is, can 2 extremely different strategies interoperate? We took the extremely strong deep types via natural and the very weak shallow types via transient. And we've shown, yes, they can interoperate, and it's the way that preserves their guarantees, improves the performance trade-off, and also, in the case of typed racket, we can now express additional programs by adding this option with shallow types. More generally, we've seen that these strategies lie along a spectrum. It's not just typed to untyped, but it's typed, untyped to shallow typed to deep typed. And so knowing about this spectrum space raises new questions to explore in the future. For one, are there other regions along here that we haven't investigated besides the deep guarantees and the shallow guarantees? Are there other points that can interoperate, and perhaps that can do so without these wrappers sitting between them? And then a third issue is we currently have a n-squared interoperability problem. There's 3 languages, and they all need to know about one another to some extent. Can we solve that in the future? So lots to explore. It's a whole new space in gradual languages, and I thank you for your attention.
So I have one to start. So on the spectrum, do you think there's particularly fruitful regions to explore?
Yes. So the big issue with transient is that there's no way of remembering what we learned about the value. Since values just flow across the boundary and there's no annotation, there's no wrapper, we need some kind of semantics with a lightweight way to remember this, and then we would have better interoperability, I think, with less overhead at the boundary.
This is really interesting. Thanks for a great talk. I'm wondering if this sort of suggests ways that as we use gradual typing to transition untyped code bases into typed ones, either by adding types or by just putting in new modules, if it suggests that we might be able to compile the code differently depending on how much of the code base has been typed in order to get presumably better expressiveness and performance guarantees.
Okay, so you're suggesting to do this automatically instead of having the programmer tune the switch?
Possibly, if it
Yeah,
suggests
no, I
ways
think
to
that would be
look at that sort of
excellent,
thing.
yeah.
Yeah.
It's a great idea.
Okay, cool. Thanks.
Yeah, thanks for the nice talk. I was wondering, so you have this picture where you show how you can go from typed to untyped and untyped to shallow and deep typed. And so there's obviously a path from deeply typed to shallow typed through untyped. So can you say something about the difference between going that path or going directly? Or you say only you do
The path is just what I showed on the picture. So the arrows are labeled pretty correctly. Yep.
Yeah, so
So which one?
So how does 3 differ from 1 composed with 2?
Yeah, 3 and 1 are the same.
Right, okay, so the point is that you can go directly and you don't need these shape checks if you want to go from deep to shallow or the way back.
Yep, the shake checks would be redundant in that case.
I see. Okay, thank you.
Hi, thank you so much for your talk. It was super interesting. In other papers I've seen where the goal is to get different languages to collaborate in one common setting, I think it's sometimes framed as compiling each of the languages into the union of the languages. And in order to get these safety properties, we sometimes just prove that these compilers into the big language are fully abstract. Have you thought about that as an alternative means for making these proofs?
Yes and no. I think full abstraction is not where you want to go for this. I think full abstraction is going to break down once you have very interesting types. Polymorphism.
Mm-hmm. Thank you.
Yeah.
Excellent talk. Thank you so much. In the presentation here, it looked like you were discussing your sort of separations in terms of like modules or compilation units. Have you looked at tighter granularities on that? Can you just say like, I want this type to be deeply typed and I want this type to be shallowly typed?
Yeah.
Have you looked at this? Does it work?
No, this is another exciting place to explore in the future. Right now, we're just at the module level granularity. So when you're using this system as a programmer, you say at the top, my whole module going forward is either deep typed or it's shallow typed. But yeah, finer granularity would be exciting, and it would be interesting to see if there's new challenges that we haven't anticipated moving to that space.
Sweet. Thank you.
All right, let me do a quick check to the Slack just to see if there's a question. I don't want to leave the virtual folks out. No questions from Slack. So let's thank Ben again.